Today we'll be exploring N-type semiconductors, an important topic in grade 12 physics. Let's first understand what semiconductors are and why they're so important in modern technology. Semiconductors are materials that have electrical conductivity between that of conductors like metals and insulators like glass or rubber. They're incredibly useful because their conductivity can be controlled by adding impurities, applying an electric field, or even by exposure to light. The most common semiconductor material is silicon, which is found in sand and is the second most abundant element in the Earth's crust. In a pure silicon crystal, each silicon atom forms covalent bonds with 4 neighboring silicon atoms. Each silicon atom has 4 valence electrons in its outer shell, and it shares these electrons with its neighbors to form a perfect tetrahedral crystal structure. However, pure silicon is not very useful as a semiconductor because it has few free electrons to conduct electricity at room temperature. This is where doping comes in. Doping is the process of deliberately adding impurities to a semiconductor to change its electrical properties. For N-type semiconductors, we add atoms with 5 valence electrons, such as phosphorus, arsenic, or antimony, to the silicon crystal. Let's see what happens when we add a phosphorus atom to our silicon crystal. Phosphorus has 5 valence electrons in its outer shell. When a phosphorus atom replaces a silicon atom in the crystal, 4 of its valence electrons form covalent bonds with neighboring silicon atoms, but the 5th electron has no bond to join. This extra electron becomes loosely bound to the phosphorus atom and can move relatively freely through the crystal structure, creating a negative charge carrier. That's why it's called N-type, and for negative charge carriers. Let's understand N-type semiconductors from an energy band perspective. In semiconductor physics, we often use energy band diagrams to represent allowed energy states for electrons. The upper band is called the conduction band, where electrons are free to move around. The lower band is the valence band, where electrons are bound to atoms. The gap between these bands is called the band gap. Electrons need enough energy to jump across this gap. In N-type semiconductors, the extra electrons from the dopant atoms create energy states very close to the conduction band, which means even at room temperature, many electrons can gain enough thermal energy to jump into the conduction band. Let's discuss the benefits of N-type semiconductors. First, they have significantly higher electrical conductivity than pure semiconductors because of the abundance of free electrons. Second, when N-type semiconductors are combined with P-type semiconductors, they create PN junctions, which are the fundamental building blocks of many electronic components, such as diodes, transistors, and integrated circuits. N-type semiconductors are essential in solar cells, LEDs, computer chips, and virtually all modern electronics. Let's summarize what we've learned about N-type semiconductors. N-type semiconductors are created by adding pentavalent dopants, atoms with 5 valence electrons, to pure semiconductor materials like silicon. The extra electron from each dopant atom becomes a free negative charge carrier, significantly increasing the semiconductor's conductivity. They are crucial in modern electronics and are widely used in combination with P-type semiconductors to create electronic components like diodes and transistors. Understanding N-type semiconductors is essential for grasping how modern electronic devices function.